Hey folks, it's Mr. Ray here. We're going to continue on with our advanced functions trigonometry unit. We're going to be talking about compound angle formulas. So compound angle, the word compound means more than one. So we're either going to be adding two angles or subtracting two angles and figuring out the formulas that relate the new angle, either the two angles added or subtracted, how that relates back to the original two angles and their sine and cosine and tan functions. So these will be formulas that you probably have to memorize. I'll give you some shortcuts and hopefully you'll see some patterns that will help you. So we're going to be using this information when we get to trig identities, which is the next lesson. And there's also some types of questions you could see that are related to these formulas that I've included on this lesson. So once you see those three and then start to be able to use them for proving trig identities, that'll be the main purpose of this lesson. Okay, so like I mentioned, compound angle is an angle that's created by adding or subtracting two or more angles. We'll just be looking at two. A double angle it's basically a special case of when you're adding two angles, but the angle happens to be the same angle in both cases, so you're basically doubling an angle. Okay, and we've got these two, we call them cofunction identities, and again, this is something that can be used with trig identities in the next lesson. You won't really see it being used in the examples for today's lesson, but it basically allows you to, if you wanted to change a sine of an angle into a cosine, this allows you to do that, or vice versa, cosine into sine. So basically, sine of x is equal to cosine of pi by 2 minus x, and the opposite, cosine x, is equal to sine of pi by 2 minus x. And you can see that pretty clearly if I just create a right angle triangle here. I've got my right angle here, I've got my angle x, and the third angle, think about that right angle as pi by 2, 90 degrees. So the sum of these two has to be 90 degrees, or pi by 2. So if that's x, then that has to be pi by 2 minus x. So for example, if I looked at, let's look at this one here, the sine of x. So I'm looking at this angle here as my reference angle. So sine is opposite over hypotenuse. So it's basically this side over this side. And if I did cosine of this angle, pi by 2 minus x, that's the cosine is adjacent over hypotenuse. So it's the same side over the hypotenuse. So you can see that both of these ratios are using the same ratio of sides, and you can see the opposite as well with the other direction. Okay, so it's kind of like I could plug a value in here. For example, if I went back to degrees for a second, the sine of 60 is equal to the cosine of 30. As long if the two angles add up to 90 degrees, the sine's equal to the other angle's cosine. Sine of 20 equals cosine of 70, and you can relate that back to radians as well. Sine of pi by 6 is equal to cos of pi by 3. Those two angles add up to pi by 2. Okay, so like I said, I'm not going to be referring to that identity in this lesson, but it will be there for trig identities as well. Okay, so here we get into the actual compound angle formulas. So you can see we have that grouped into three sections. We've got addition formulas where we're adding two angles together and then taking the sine, cosine, or tan. The second group, we're subtracting two angles, and the third one, it's sine of a double angle, so 2 times x. So this is just a special case of the addition formula. So if I just replaced the y with x, that would be sine of 2x, and then you see sine x cos x, etc. Anyways, these are the formulas. I did include on the lesson a link to a video that that proves this addition formula. There's lots of formulas here. I just wanted to show you one so you can see how it's actually proved that this is true. And the other proofs would be a similar nature. You don't have to be able to prove it. I just, for those of you that are mathematically inclined and don't want to take my word for it as to why this may or may not be true. So for those students in that position, I would recommend looking at that video. It's quite interesting actually. Okay, so you can see that when I do the addition formulas, it breaks the formula into the sines and coses of the individual angles and multiplies and adds in a combination listed here. So basically, if I want to know any of these, I need to have sine x, sine y, cos x, and cos y. I need to have all four values in order to come up with the value for these. And similarly for tan, if I want to know the tan of the combined angle, I need to know the tan ratio of the individual angles. Okay, and then there's similar formulas for subtraction. You can see that they're related. For example, sine x plus y, sine x minus y. I got the same terms: sine x cos y, sine x cos y, cos x sine y. The only difference is it's turned into a subtraction sign. And you can see similar patterns for the other two. So, I don't want you to have to memorize all 6 of these. Hopefully you just remember the relationship to maybe just understand these and know the pattern to come up with the subtraction formulas. And like I said, the double angle formulas, for sure you should not memorize these, because like I said, it's really just taking the addition formulas. And for example, sine of 2x, replace the y with an x here, here, and here, and that turns into it turns into sine x cos y plus sine x cos y plus, let me start again. It turns into sine x cos x plus cos x sine x, which is the same thing. So you get this formula here: 2 times sine x cos x is the shortened, abbreviated version of that formula. If we did the cosine of a double angle, again, we're replacing y with x, so we get cosine of 2x. And if I replace the y with x, I get cos x cos x, which is cos squared x. And here I'm going to get sine squared x, so cos squared x minus sine squared x. There's actually 3 formulas here. This is the one that comes naturally from the addition formulas. But if we bring in this, the trigonometric identity, sine squared x plus cos squared, that should be an x there, is equal to 1. This is basically the Pythagorean identity. What we can do is we can isolate sine squared x as 1 minus cos squared x, and cos squared x is 1 minus sine squared x. Hopefully you remember that. You'll be using these a lot in the trig identities. So if I just came up with a new version, if I replace cos squared x here with 1 minus sine squared x, that turns into 1 minus 2 sine squared x. And similarly, if I replace the sine squared x with 1 minus cos squared x, I'm gonna get this second version here. So again, I wouldn't want you to memorize any of these, but you can definitely get them by substituting in for these isolated values here. Okay, and then the tan of the double angle, just simply you change the y angle to x, so tan of 2x would be tan x plus tan x, which is 2 tan x, and then you get 1 minus tan x, which is 1 minus tan squared x. Okay, so these are the formulas. We're going to be applying them in a few different circumstances. So let's see how we can do that. Now, unlike the other lessons, I've got the work already done because this is my second attempt at the lesson. had some audio problems, so maybe I can just kind of hide so we can focus on each step. Okay, so the first example, what we're doing is we're using these compound angle formulas to find an exact value. This is not rounded to the nearest 2 decimals. It's exactly. So we'll, for example, if I want to find the cosine of 15 degrees, so we'll start off with a degree question. Okay, if I was to look at the unit circle, there's no special angle of 15 degrees, so I wouldn't know how to do it, but we could just rewrite cos 15 as either a sum or difference of 2 of the angles that are already on the unit circle. So, and those are multiples of 30 and 45 as you go around. So how could I create a 15 degrees? Well, this takes a little bit of thinking, hopefully not too much. And you could say, well, isn't 15 degrees is really 45 minus 30. So I've rewritten this cos 15 as a compound angle, a subtraction, 45 degrees minus 30. So we could then go back. Let me go back to the sheet here. So that's the cosine, and that's the difference subtraction formula. So I'm going to basically rewrite cosine of 45 minus 30. I'm going to replace the x's with 45 and the y's with 30. Okay, and I come up with this. So you can see I've got, this is like sine x cos y plus, it's cos x cos y plus sine x sine y. And I put those in, and these are values, all 4 of these values are values that we know from the unit circle. So I replace those in the brackets here. So cos 45, 1 over root 2, same thing with sine 45. Cos 30 is root 3 over 2, and sine 30 is 1 over 2. And so we multiply each of the pairs. We get this, root 3 over 2 root 2, and 1 over 2 root 2. They have the same denominator. Combine them together, we get this. Now, for these types of questions, I definitely want you to rationalize the denominator, which means no radical signs in the denominator, no roots. So this one's not too hard to get rid of. We'll just multiply top and bottom by root 2 over root 2, which is basically multiplying by 1. But you can see when I multiply this time, it's going to be root 6 plus root 2 over the root 2 times root 2. That's just works out to be 2. 2 times 2 is 4. So this is an exact value. And we couldn't do this before on the unit circle because we didn't have special angle for 15. But it turns out if we can use the compound angle formulas, we can come up with some more angles that we can get the exact value for. So it turns out what we'll be able to add is any multiple of 15. So angles like 15, 75, 105, etc. Okay, so let's switch over to, we'll do a radian question. So in this case, they want to know the exact value for tan of 5 pi by 12. Well, that definitely wasn't on the unit circle, so we're going to convert it into a sum or difference of 2 angles. Now, if you're like me, you always think in degrees. So I'm going to do a little side work over here. It shouldn't be part of my main question. And you can't do this in degrees in the question and convert to radians at the end or whatever. You have to basically do the work on the side here. So 5 pi by 12, I can just multiply this by 180 over pi, and I get 75 degrees. So now I'm thinking, well, how can I create 75 degrees by adding or subtracting 2 angles that I know on the unit circle? And it's very similar to what we just did. Instead of subtracting these angles to get 15, we're going to add them together to get 75. Okay, so I'm going to basically rewrite and then convert 45 degrees back to radians, pi by 4, 30 degrees is pi by 6. So I can rewrite this as a sum of these two angles. So that's a formula. If you go back to our sheet, okay, so remember, we're going to be using this formula here, tan of x plus y. So we're going to be adding together the two tans and then subtracting the product from 1. So just replace the x and y with pi by 4 and pi by 6. So there we go. We've done that conversion, and we know that tan of pi by 4 is 1, tan of pi by 6 is 1 over root 3. So we've got the same values down here. So when we start simplifying this one's a bit trickier. So 1 is the same as root 3 over root 3, so that's root 3 plus 1 over root 3 on the top. And same thing on the bottom, we got root 3 over root 3 minus 1 over root 3. So we get on the denominator root 3 minus 1 over root 3. The root 3's on the bottom cancel out. So we just have root 3 plus 1 over root 3 minus 1. And again, we have that issue with a radical in the denominator. We want to get rid of the root 3. Now, we can't do it just by multiplying by root 3, because it'll fix this, but it'll create another root when I multiply it with that. So we actually do something called rationalizing the denominator by multiplying by the conjugate. So the conjugate is, and this is when you have a binomial on the denominator, so we multiply by exactly the same binomial, except we switch the sign in between the terms, and of course we have to multiply by that on the top as well. So if you look at these two things here, it's basically like a difference of squares in terms of the factors. You got a minus b, a plus b, so it turns out to be a squared minus b squared. In this case, root 3 squared minus 1 squared. Root 3 squared is 3, subtract 1. So that's nice, because now we just got 2 on the bottom. We still have to do our FOIL on the top. So we get root 3 we get plus root 3 plus root 3. So we get plus 2 root 3 and then plus 1. We can combine the 3 and the 1 together. So we end up with this. And then you can see, well, I got every term here I can divide by 2. So if I divide the top by 2 and the bottom by 2, I get, well, 1 on the bottom and then just 2 plus root 3. So this is the exact value of tan of pi by 3. Sorry, tan of 5 pi by 12. So you can see here that the way we applied the compound formulas is we're able to come up with exact values of, well, it turns out to be multiples of pi by 12 if we're looking in radians. If we're looking in degrees, it's multiples of 15 degrees. So we now have a whole bunch of new angles we can get the exact trig ratios for. Okay. The other way we can use the compound angle formulas by looking at the raw formulas is in the other direction, which I've stated here. So what does that mean? Well, instead of just being given, cosine of x plus y, and then putting in the expanded formula like we did up here. Well, what if we had a question where we had the expanded formula and we wanted to simplify it? So something like this. It looks pretty complicated, but hopefully the first thing you notice, you've got two angles repeating. Make 7 pi by 12 and 5 pi by 12. So let's temporarily call them x and y. So I got x, y, x, y. So now I can look, do I have a formula for cosine x, cosine y plus sine x, sine y? Well, of course I do. That's the cos of x minus y formula. So once we've got that, you can see now we're going the opposite direction. I'm taking this expanded version of the double angle formula with the single angles, and we're converting it into the double angle for the cosine x minus y. So I replace the x with 7 pi by 12 and the y with 5 pi by 12. Subtract, I get 2 pi by 12 or pi by 6. And cosine of pi by 6, that's directly off the unit circle. So you can see this one's a lot quicker because you're just kind of simplifying the angle in the brackets by adding or subtracting. Okay, the other example here, again, very similar. We've got this expanded formula here with single angles in the brackets, but two different angles, 3 pi by 5, pi by 15, call them x and y, x and y. And do I have a formula for sine x cos y plus cos x sine y? Yes, we do. That is the sine of x plus y formula. So basically I replace the x with 3 pi by 5 and the y with pi by 15, add them together inside. So I need a common denominator this time. So 3 pi by 5 is the same as 9 pi by 15. Add them together, I get 10 pi by 15, which is really, I can divide top and bottom by 5. I get sine of 2 pi by 3, which is from the unit circle, root 3 over 2. So that's the second way we can apply using those formulas. It goes in the opposite, the other direction, where we turn it into the double, into the formula with the two angles together, either added or subtracted. Okay, so I've got one more example here. Okay, and I've got the work already done again, so let's look at this. So this question's a little bit more difficult. Once you've seen one, you'll know how to do other ones. We've got angle A. Well, angle A is in the second quadrant and angle B is in the first quadrant. So there's where angle A might be, first quadrant. There's where B is. So there's A, there's B. So we're actually, eventually we're going to be using the compound formula. But there's some leading questions that are going to help us figure out how to do it. So they've given us a ratio for both of the angles. They've given us a sine ratio for A, and we know it's 5/13. They give us the cosine ratio for angle B. We know it's 3/5. Okay, and the first part is determine exact value for cosine of A. So what we have to do here, write out what we know about angle A. We know sine of A is 5/13. That tells us, remember the sine ratio is y over r. So it tells us y is 5, and it tells us r is 13. Okay. Now, in terms of the sine, we always know that r is positive. So there's no doubt that that r is positive 13 and a is 5. Okay. So we write that down, and what we need to do, if we want to come up with the cosine of a, that formula is x over r. Well, we know r from the above ratio, but we don't know x. So this is done later. So we actually use Pythagorean theorem. We know the Pythagorean theorem is x squared plus y squared is r squared. We know y, we know r. So we plug those in. We square them, we get 25, 169. Subtract 25, x squared is 144. Take the square root, it's plus or minus 12, right? Okay, but here's where an important piece of information comes in that we haven't really looked at, although we said it. We know that angle A is in the second quadrant. Okay, so second quadrant is right here. So this is where you could use your cast rule or just know the fact that x is positive here, negative over here. So that means cosine is positive in these two quadrants. It's going to be negative in these two quadrants. So rather than just guessing and saying it's plus 12 or minus 12, we know that since it's in second quadrant, we know that cosine has to be negative there. So the value of x is negative 12, and then we plug it back over here. So the cosine of A is negative 12/13. So that answers the question in A. Similar style question, part B. Determine exact value for sine B. They told us cosine B was 3/5, which tells us, well, cosine is x over r. So x is 3, y is 5. But if we want to know what sine B is, we have to know what y is. So again, we do Pythagorean theorem again. Plug in 3 and 5. Subtract 9 from both sides. Y squared is 16. So y could be plus or minus 4. But we know that angle B is in quadrant 1. So quadrant 1, all the ratios are positive there. So we know that in this case y has to be positive 4. And then just plug it in over here. So sine B is 4/5. Okay. So you might be asking, well, why are we doing all this other than the fact they asked us to? So this is kind of setting us up for this question. Determine an exact value of sine of angle A minus B. Okay, so this is obviously the subtraction formula for sine. So I've just put that in here. And like I said at the beginning of the lesson, so we have to know the sine of A, the cosine of A, the sine of B, and the cosine of B. We have to know all four ratios. Well, thanks to the above questions, we added the two that we didn't know. We didn't know sine B or cos A, but now we do. So we can go ahead, plug in the values we're given plus these values. Okay, and then just simplify. So I've got 15 over 65 minus negative 48 over 65, so that's plus. Add the tops together, we get 63 over 65. So this is an exact value. Okay, and hopefully you can see how this would be done. They could have just as easily asked us any one of the other three ratios for sine or cosine. If they asked us something with a compound angle formula for tan, we just have to figure that out based on coming up with the ratios that we might be missing from what they gave us. Okay, so that's it for this lesson. Got some homework for you to look at. Don't forget, I've also got the video. It's a Khan Academy video that shows you the proof of the formula for sine of x plus y. Just give it a little look just to see where they did it. It's quite interesting. But again, you don't have to be able to show me that. It's more out of curiosity that I put it up there. So the next lesson will be looking at proving trig identities. So we're going to extend what we did in grade 11. Going to be adding a lot more identities, including the ones from this lesson, and also the one I showed you at the beginning, the co-identity, cofunction identities here. So we've got a whole bunch of new identities on this first page that we can now add to our list from grade 11. So that's going to lead to a whole bunch of more difficult identities to try to prove. Okay, so we'll be looking at that next lesson. So until then, I hope you have a good day, and we'll see you in a couple of days.